Something is happening right now in the world of computing that most people outside the tech industry have barely noticed, but it's reshaping everything from the phones in your pocket to the data centers powering AI. We're talking about a full-scale war over computer chip architecture. Not the kind of war fought with missiles, but one fought with transistors, software ecosystems, and trillion-dollar infrastructure bets. For the better part of 4 decades, two chip architectures divided the computing world between them, x86 and ARM. And for most of that time, the outcome felt inevitable and permanent. That status quo is now collapsing. In this video, we're going to walk through how we got here, why the old duopoly is cracking, and what a new open-source architecture called RISC-V means for the future of computing, from your smartwatch to a satellite in orbit. This is a purely educational explainer, and nothing here should be taken as financial advice. Before we can understand where computing is going, we need to understand the stakes of why this moment matters so much. The world is in the middle of a once-in-a-generation AI infrastructure build-out, and data centers are consuming power at a rate that is genuinely alarming grid operators and governments. A single large AI training cluster can consume as much electricity as a small city, and projections suggest global data center power demand could double or triple within this decade. That means every watt saved at the chip level translates directly into billions of dollars in operating costs and real-world carbon emissions. The chip architecture war isn't just about performance benchmarks anymore. It's about energy and money. To understand the revolution, you first need to understand the old order. For roughly 4 decades, the computing world was split cleanly in two. On one side, you had x86, the architecture Intel and AMD built their empires on, which ran every PC, laptop, and server that mattered. On the other side, you had ARM, a British architecture that conquered mobile. Every iPhone, every Android phone, every tablet ran on ARM-based chips. These two architectures weren't just technical standards, they were massive economic moats protected by decades of software, developer tooling, and corporate inertia. You wrote software for x86 servers or ARM phones, and that was essentially the only choice that made sense. The rest of the industry, from Microsoft to Google to Amazon, built their entire businesses on top of this duopoly and largely accepted it as a law of nature. So why is x86 losing ground? The short answer is that the architecture carries 4 decades of baggage, and, in a world obsessed with power efficiency, that baggage is expensive. Here's the clearest way to think about it. x86 instructions come in variable lengths, like sentences of wildly different word counts, all jumbled together in a single paragraph. Before the processor can actually do any work, it has to spend time and energy just figuring out where each instruction starts and ends, chopping up that messy stream into bite-sized pieces. This decoding process alone consumes a meaningful chunk of the chip's power budget. ARM, by contrast, uses fixed-length instructions. Every single one is the same size, like a perfectly uniform stack of building blocks. The processor can grab and process them in neat, predictable batches far more efficiently. And this isn't a minor footnote, that x86 decoding overhead can consume up to 10% of total package power, while also limiting how many instructions the chip can start processing simultaneously. The clearest proof that x86's dominance was about software lock-in rather than raw architectural superiority came from Apple. In 2020, Apple announced it was abandoning Intel x86 chips entirely and switching its entire Mac lineup to its own ARM-based M-series silicon. The tech world expected a painful, multi-year compatibility nightmare. Instead, Apple shipped a translation layer called Rosetta 2 that let old x86 software run on the new ARM chips. And it worked so well that most users couldn't tell the difference, with only about a 9% performance penalty during emulation. That number is remarkable. It means the underlying ARM architecture was so much more efficient that it could carry the overhead of translating an entirely different instruction set and still match or beat the original Intel chips in real-world performance. The transition was essentially complete within 2 years, and it sent a message that reverberated through every hyperscaler, every cloud provider, and every chip designer on the planet. The software mode around x86 was crossable. The hyperscalers Amazon, Google, Microsoft were watching Apple's transition very closely, but they had their own, even more pressing motivation, their electricity bills. When you're running millions of servers, a 30 to 40% improvement in price performance per chip isn't a nice-to-have, it's a transformational cost advantage. Amazon was the first to move at scale, building its own ARM-based chips called Graviton, and the numbers they published were striking. In cloud database workloads, AWS found that Graviton instances delivered up to 60% higher throughput and 35% lower latency compared to equivalent x86 instances, with infrastructure cost savings in the range of 30 to 35%. These aren't benchmark lab results. These are production workloads running at massive scale. And once Amazon proved it worked, Google, Microsoft, and virtually every major cloud provider accelerated their own ARM programs. The data center, long assumed to be x86's permanent home turf, had its door kicked open. So x86 is losing ground to ARM, but does that mean ARM wins? Not necessarily, because ARM is creating its own problems that are driving the industry toward a third option. Here's the business reality. Every company that designs an ARM-based chip has to pay ARM Holdings a royalty anywhere from 10 cents to $2 per chip, depending on the device category. For a company shipping hundreds of millions of IoT sensors or automotive microcontrollers, that royalty line adds up to serious money. But beyond the royalty cost, ARM Holdings has been aggressively escalating its terms under its current ownership, pushing chip designers to license broader IP bundles and, in some cases, attempting to charge royalties directly to device makers rather than just chip designers. This culminated in a high-profile legal dispute with Qualcomm that captured the industry's attention. The specifics of the legal timeline aren't what matter here. What matters is the signal it sent. Major tech companies, Qualcomm, Google, Samsung, Nvidia, began accelerating their own RISC-V investments precisely because they wanted an architectural escape hatch from ARM's licensing grip. This brings us to the second act, RISC-V. The name stands for Reduced Instruction Set Computer, version 5, and it originated at UC Berkeley as an academic project around 2010. What makes RISC-V fundamentally different from both x86 and ARM isn't just that it's more efficient or more elegant, it's that nobody owns it. The RISC-V ISA is an open standard maintained by a nonprofit called RISC-V International, and any company or government can implement it, modify their implementation, and ship products based on it without paying a single dollar in royalties to any gatekeeper. This is structurally analogous to what Linux did to proprietary Unix in the data center. Linux didn't win because it was dramatically better on day one, it won because it was open, free, and composable in ways that proprietary alternatives could never be. RISC-V is following the same playbook, and it's following a trajectory that looked remarkably similar to ARM's own history, conquering the low-end embedded and IoT market first, then scaling upward as the ecosystem matures. For RISC-V to graduate from embedded microcontrollers to real servers and AI systems, it needed a standardized feature baseline, a common language that software could target reliably. That's exactly what the RVA23 profile provides. Think of it like USB-C for chips. It defines a consistent set of capabilities that every compliant RISC-V processor must support, which means software authors can write once and run anywhere that implements the standard. The impact of RVA23 is most visible in two headline developments. First, Canonical announced that Ubuntu 25.1 and 26.04 would target RVA23 as their baseline, which means the most widely deployed Linux distribution in server environments will run natively and optimally on RISC-V hardware. Second, and perhaps more consequential, Nvidia announced it was porting CUDA, the dominant programming framework for AI and GPU computing, to the RVA23 profile. That means RISC-V CPUs can serve as the primary host processor in AI training and inference systems, potentially eliminating the dependency on x86 or ARM host processors entirely. These aren't roadmap promises, they're ecosystem inflection points. Let's talk about where RISC-V hardware actually stands today in competitive terms, because this is where the rubber meets the road. For years, RISC-V had plenty of excitement but limited commercial-grade silicon in high-performance categories. That's changing rapidly. SpaceMIT's VitalStone V100 is a 64-core RVA23 compliant server chip that represents the first commercially competitive RISC-V data center hardware. SpaceMIT also has edge AI chips, the K3 and K5, delivering 60 to 120 trillion operations per second for on-device AI processing, which puts them in credible territory for inference workloads at the network edge. And Tensorant, the AI chip startup backed by some of the same people who built the chips inside your iPhone, is building its next-generation AI accelerators on RISC-V cores called Ascalon. These aren't hobbyist projects or research demos, they're commercial products targeting real market segments. The hardware ecosystem is moving from proof of concept to production faster than most mainstream observers expected. Now let's talk about Intel, because Intel's story in this architectural transition is one of the most ironic in modern tech history. Intel built its entire empire on x86. For 30 years, if you wanted the fastest computer in the world, it ran Intel inside. But today, Intel finds itself in a genuinely precarious position. Its x86 product lines are under pressure from ARM in servers and data centers. Its manufacturing process has fallen behind TSMC and Samsung. And it's scrambling to reinvent itself as a contract chip manufacturer, a foundry, under the Intel Foundry Services brand. The new manufacturing nodes, particularly 18A featuring ribbon-FET transistors and power via backside power delivery, offer real technical merit, roughly 30% better density and 25% higher frequency at the same power level. But here's the existential irony. The customers Intel is courting for its foundry business are exactly the companies designing ARM and RISC-V chips to replace Intel's own x86 products. Intel's survival strategy requires manufacturing the very architectures that are killing its core business. Let's take a step back and look at the broader trajectory of where computing is headed. For most of computing history, the CPU was the center of the universe. Everything else was a peripheral. But in an AI-dominated world, that model has inverted. The GPU, or AI accelerator, is now the primary compute engine. And the CPU has been demoted to a data orchestration role, scheduling tasks, moving data in and out of memory, managing I/O. When the CPU is primarily an orchestrator rather than the main worker, the specific instruction set it uses matters much less. And what matters much more is power efficiency, cost, and the ability to customize the chip for your specific data pipeline. This is exactly why we're seeing a heterogeneous compute paradigm emerge, where the ISA choice is driven by workload requirements rather than legacy software lock-in. x86 is being relegated to the segments where its software compatibility still commands a premium, primarily Windows Enterprise environments, while ARM and RISC-V expand everywhere else. Let's zoom out and look at the competitive landscape across all three architectures in terms of where each one sits today and where they're heading. x86 isn't dying tomorrow. It has enormous installed base momentum, particularly in enterprise Windows environments, legacy financial systems, and anywhere that running decades-old compiled software is a hard requirement. But its growth trajectory is clearly plateauing. ARM has already won mobile, is winning the cloud server market on price performance, and is making credible inroads into laptops and desktops via Apple's M series and Qualcomm's Snapdragon X Elite. RISC-V is the most open question. It's clearly established and embedded in IoT, is gaining momentum in automotive and edge AI. And the RVA23 Plus software ecosystem developments are the first credible indication that data center adoption is a realistic medium-term outcome rather than a distant theoretical one. The key thing to understand is that this isn't a zero-sum game that produces one winner. It's a transition from a two-player duopoly to a richer, more differentiated landscape. So what does all of this mean if we try to look out to the early 2030s? The thesis here isn't that x86 disappears overnight. It won't. The thesis is that x86 transitions from being the default computing standard to being a premium niche architecture. Think of it like mainframes. They didn't die. They became highly profitable, specialized tools for specific use cases, while the rest of computing moved on around them. ARM is likely to consolidate its position as the dominant general-purpose architecture across mobile, cloud, and eventually desktop, though it faces a genuine threat from RISC-V in the cost-sensitive high-volume markets where its royalties become a meaningful margin factor. And RISC-V is following a trajectory that mirrors ARM's own history in the 1990s, starting at the bottom of the performance and complexity ladder, standardizing rapidly, attracting hyperscaler and ecosystem investment, and climbing steadily upward. The open-source ISA is structurally positioned to do to the CPU layer what Linux did to the operating system layer: commoditize it, democratize it, and make the idea of paying a gatekeeper for access to it feel increasingly archaic. To bring everything together, we've watched a 40-year duopoly between x86 and ARM start to fracture under the combined pressure of AI infrastructure economics and power consumption constraints. The architectural inefficiencies that x86 has carried since 1978 are no longer an acceptable cost when you're trying to power exabyte-scale AI systems on a finite energy budget. ARM has proven that the software moat around x86 is crossable. Apple did it in 2 years. And Amazon is doing it at cloud scale right now. And RISC-V, the open challenger that nobody owns and nobody can sanction, is climbing the performance ladder faster than most expected, enabled by standardization milestones like RVA23, software commitments from Canonical and NVIDIA, and a geopolitical tailwind that has an entire nation-state investing in its success. The era of one architecture ruling computing by default is over. What replaces it is a richer, more competitive, and ultimately more efficient landscape. And understanding it is essential for anyone trying to make sense of where technology is heading over the next decade. That's a wrap on the chip architecture war. We covered a lot of ground, from the fundamental physics of why x86 decoding costs you power, all the way to Chinese state-backed RISC-V silicon and the geopolitical battle over an open instruction set standard. If you made it this far, you genuinely understand one of the most consequential technology transitions happening right now. If there's a specific piece of this you'd like me to go deeper on, whether that's the Intel Foundry situation, the SA-AFIAC debate, or the specific RISC-V hardware landscape, Drop it in the comments and I'll prioritize it for a future video. And if you found this useful, sharing it with someone else who'd find it interesting is genuinely the best way to support the channel. Thanks for watching, and I'll see you in the next one.